Now look at question 9, which says we have to explain the meaning of diamagnetic and paramagnetic. So I think this focuses on a concept of electrons being paired. Of course, Pauli exclusion principle tells us that no two electrons can have the same or set of 4 quantum numbers. Okay, so in a single orbital, we know an orbital can have 2 electrons only. One is supposed to face upwards, the other one downwards, indicating that the magnetic spin quantum number is different. The one facing up is positive half. So all the other 3 set of quantum numbers would be the same, but the fourth one would be different. Okay, so now the argument is, in a case where you have, let me give an example of 1s, 2s, and then let's talk about 2p. So in a case where you have electrons just being like that, where they are not paired, where there's only a single electron in a given orbital, that is said to be paramagnetic, meaning that electrons are not paired fully. And then the magnetic focuses on a case where they are paired. When electrons are fully paired, that is said to be diamagnetic. And of course, there's a bit of some attraction, weak attraction to paramagnetic, and then diamagnetic, there's no attraction, no weak attraction at all that can actually be observed. Okay, so I've said diamagnetic refers to unpaired electrons, okay, and are not attracted to any magnetic field. So all the electrons are paired. Then for paramagnetic refers to they have unpaired electrons. So diamagnetic does not have any unpaired electrons. Paramagnetic does have unpaired electrons, which are weakly attracted to a magnetic field. So examples would be, let me give simple examples. I think that would be helium for diamagnetic and then oxygen for paramagnetic. So of course we know oxygen, for example, has got that's 6, right? That's the atomic number of oxygen. Is it 6 or 8? It's 8 actually. So it's 8. And then if you try to substitute, we're going to have 1, 2, 3, 4. And then how many more do we need? So we have 4 already. So 5, 6. So we have 6, and then 7, and then 8. So see, there are 2 electrons that are unpaired there. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So there are 2 electrons that are unpaired there. So this makes this to be paramagnetic. Okay, there's a set of electrons that are unpaired. For diamagnetic, no electrons are unpaired. Of course, helium should be the second. Okay, so only 2 electrons which are paired. So this makes it to be diamagnetic. So it's not attracted to, there are no weak attractions to a magnetic field. Okay, so whenever you want to tell whether a specific atom, is like diamagnetic of any element, just try to, fill in the orbitals like I've did there. It will show. Okay. So the ground state electron configurations listed here are incorrect. We need to explain what mistakes were actually here. So I would advise you get your periodic table and then get the atomic number of these atoms and then try to write our own so that we can easily identify the mistakes. So starting with atomic number of aluminium. So atomic number of aluminium is 13. And then atomic number of that should be boron, right? Boron 5. Then atomic number of fluorine, that should be 7. Fluorine. So atomic number of fluorine is 9. Okay, so if you've watched our video, that is the introduction to introduction to the study of the electron configurations. I already showed you on how you can come up with electron configuration. So 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. So I said this is the way you move from 1s to 2s, 2p to 3s, 3p to 4s, 3d to 4p, like that. So we'll start. How many electrons do we have for aluminium? 13. So 1s2, 2s2, 2p, p gets 6. So how many do we have already? 2, 4, 6. Are we done? 6 plus 4, 10. We're remaining with 3. So now go to 3s and then 2. Are we done? So 2, 4, 10, 12. And then you can go to 3p1. Okay, so that already tells you what is paramagnetic, right? Boron, 1s2, 2s2, that's 4. 2p1, that gives us 5. Fluorine, 1s2, 2s2, 2p6, that's 10. That's already more, so we need to reduce to 5. 5 plus 4, 9, right? So that's how you come up with electron configuration. So you can see where the errors were, right? Can move on to the other question.